Derivatives of logarithmic functions. We'll start by calculating the derivative of the natural log of x. Now, we don't know the formula yet, so we have to derive it. Alright, so I'm going to let y equal the natural log of x. And so I just need to figure out what's dy dx. Alright, so I need then dy dx. Alright, so I'm going to take a slightly different approach. I'm not going to use a direct approach. Instead, what I'm going to do is I'm going to use the inverse. If y is equal to the natural log of x, then by definition, e to the y is equal to x. Now, I'll apply the differential to both sides. d by dx of e to the y would be d by dx of x. Alright, now d by dx of e to the y would be e to the y times dy dx. d by dx of x is 1. Alright, so then dy dx would be then 1 over e to the y. But y was equal to the natural log of x. So dy dx would equal 1 over e to the natural log of x. And through our cancellation properties, 1 over e to the natural log x, we find that dy dx is 1 over x. So, if our function is natural log x, its derivative is 1 over x. Alright, so again, d by dx of natural log of x is 1 over x. Now, if we need to calculate the derivative of the natural log of some function of x, we apply the chain rule. And we would have 1 over that function times the derivative of the function. Alright, so let's see a couple of examples. Here we're asked to differentiate. We have f of x is equal to the natural log of x squared. Alright, so I'm going to actually show a couple of different approaches to this. The first approach, maybe the most direct approach, so then f prime of x would be 1 over x squared times the derivative of the x squared. And so that would be 1 over x squared times 2x. And simplifying this, 1 over x squared times 2x, that would give us 2 over x. Alright, so f prime of x is 2 over x. Now, wait a second. What if I rewrote that original function? The natural log of x squared, I can rewrite that as 2 times the natural log of x, using our rules for logarithms, right? So now, then f prime of x would be, since 2 is a multiple, 2 times, and now the derivative of natural log x is 1 over x. And again, we get f prime of x is 2 over x. We get the same thing with either approach, just a matter of which you prefer. Alright, let's look at another example. Here we have f of x is the natural log of the natural log of x. Alright, let's see. So, to calculate the derivative of the natural log of something, we have 1 over the something times the derivative of the something. Alright, so f prime of x would be 1 over the something times the derivative of that same something. And so we would have the natural log x here, natural log x here. And so then that would be 1 over natural log x. Then the derivative of natural log x is 1 over x. And so then f prime of x is, we would usually write that as 1 over x natural log x. differentiate f of x is equal to the natural log of cotangent x. So let's see. Using the same idea, then the derivative would be 1 over cotangent x times the derivative of cotangent x. Alright, so let's see. 1 over cotangent x. Now the derivative with respect to x of cotangent x is negative cosecant squared x. Alright, so, I'm going to see if I can write this in terms of sines and cosines. Now, 1 over cotangent x, well, that's the same as tangent x, so that would be sine x over cosine x times negative cosecant x, that would be 1 over sine square x. Alright, so now we can remove a common factor of sine x, and so I'll write this as negative 1 over sine x cosine x. Or negative cosecant x secant x. Find the equation of the tangent line to y equals the natural log of x e to the x squared at x equals 1. Alright, so let's first figure out the point. If x equals 1, then y would equal the natural log of 1 times e to the 1 squared, and so that would be the natural log of e, which is 1. So the point is 1, 1. Alright, so we have the point. Now we need the slope. Alright, so we can calculate the derivative. Y prime would be 1 over x e to the x squared times d by dx of x e to the x squared. And now we'd have to use a product rule and a chain rule. Okay, wait a second. There's got to be a better way. So let's look at this differently. If y is equal to the natural log of x e to the x squared, then y would equal the natural log of x plus the natural log of e to the x squared. Using our manipulation of properties for logarithms. And so then y would be the natural log of x plus the natural log of e to the x squared is just x squared. Now look, that's easy to differentiate. Y prime would be 1 over x plus 2x. Alright, so there's... Now, if you were to continue with calculating the derivative from the original form, and after you go through all of your simplifications, you'll get the same thing, just maybe in a slightly different algebraic form. But this is so much easier. Alright, so we have the point, 1, 1. Now the slope. The slope would be the derivative at x equals 1, and so that would be 1 over 1 plus 2 times 1, so that's 1 plus 2, that's 3, and so then the equation of the line would be y minus 1 is 3 by x minus 1, and this is easy enough to get to slope-intercept form, y equals 3x minus 2. Alright, so if you need to calculate the derivative of a logarithmic function, you might want to consider some manipulations to put it in a form that's easier to work with. Find f prime of x if f of x is the natural log of the absolute value of x. Alright, now remember, absolute value we can think of as a piecewise defined function. Right? The absolute value of x is equal to itself, the absolute value of x is x if x is positive, but it's equal to its opposite if x is negative. And I guess I could really say, or greater than or equal to 0. So now, the natural log of absolute x I can think of as this piecewise defined function. I can think of it as the natural log of x if x is positive, and I can think of it as the natural log of the opposite of x if x is negative. Notice I'm not including 0 anywhere here because 0 is not in the domain of the natural log function. Right? The natural log of 0 is undefined. All right, now we want to calculate the derivative. All right, so if x is less than 0, then f prime of x would be 1 over negative x times negative 1, which is 1 over x. If x is greater than 0, then f prime of x is still 1 over x, because that's just the simple derivative of the natural log function that we've already discussed. So it turns out that if f of x is the natural log of the absolute value of x, then f prime of x is still 1 over x. Now, this becomes important for integration. All right, so we just showed that d by dx of the natural log of the absolute value of x is 1 over x. Then, the integral of 1 over x dx is equal to the natural log of the absolute value of x plus a constant. Okay, and so also remember that that means that the integral of x to the negative first dx is natural log absolute x plus a constant. Okay, so we now have a new antiderivative formula. We have to keep this in mind. All right, so as an example, evaluate the integral from 1 to e of 1 over x dx. Well, this would be the natural log of absolute x from 1 to e. And so then this would be the natural log of the absolute value of e minus the natural log of the absolute value of 1. Now, since both e and 1 are positive, we don't really need those absolutes, but I'm putting them there just as a reminder. The natural log of e is 1, the natural log of 1 is 0, and so that's exactly 1. Evaluate the integral from e to e squared of natural log of x over x dx. All right, now there's no sort of inside for us to try as our substitution, so this might take a little trial and error. But what I sort of notice is I see that 1 over x, and I know that 1 over x is the derivative of natural log of x. So what if I let u equal the natural log of x? If u is the natural log of x, then du is 1 over x dx. And I see that 1 over x dx. And so then I can rewrite this as an integral of u du. Wait a second, I've got to change my limits of integration. If u is the natural log of x, well, if x equals e, then u would be the natural log of e, which is 1. If x equals e squared, then u would be the natural log of e squared, which is 2. So this is from u equals 1 to u equals 2. And this is a simple integral, right? Integral from 1 to 2 of u du, that would be 1/2 u squared. From 1 to 2, I can bring the 1/2 outside, and I'd have 2 squared minus 1 squared. So that's 4 minus 1 is 3, 3/2. Evaluate the integral, integral cotangent x dx. Right, so we don't have a special formula for this integral yet. So let's derive it. We're going to derive this formula, and to do this, we're going to use an identity from trigonometry. Recall that the cotangent of x can be rewritten as the cosine of x divided by the sine of x. And so we now have the integral of cosine x over sine x dx. Now, what if I were to let u equal cosine x? Now, what if I were to let u equal sine of x? Well, the derivative of sine x is cosine x dx. And notice I have this cosine x dx. So then this integral can be rewritten as 1 over u du. And that's a simple integral. The integral of 1 over u du is the natural log of the absolute value of u plus a constant. And so then this is the natural log of sine x plus a constant. And so we now have a formula. The integral of cotangent x dx is the natural log of the absolute value of sine x plus a constant. You could evaluate the integral of tangent x dx using a similar technique. What if we wanted to find the integral of secant x dx? Now, unlike the previous exercise, this one is not a simple trigonometric substitution or an identity. This one is not intuitive. It would be difficult to figure this one out on your own. Fortunately, about 500 years ago, somebody figured it out, and it's once you see it, I'd say, well, of course, but until you've seen it, it's very difficult to think of how it would have been done. So what we do is, I'm going to take that secant x and I'm going to multiply by a particular quantity. I'm going to multiply by the quantity secant x plus tangent x over secant x plus tangent x. And this is a legal move because I'm multiplying effectively by 1. But now notice what will happen here. If I simplify this through a distributive property, I'm going to have a secant square x plus secant x tangent x in the numerator, and the denominator I'm going to leave as secant x plus tangent x. Now if you look at this, you say, well, wait a second, something familiar here. You should maybe recognize that the derivative of tangent x is secant square x, and that the derivative of secant x is secant x tangent x. So if I let u equal secant x plus tangent x, the denominator, then du is secant x tangent x plus secant square x, the numerator. And so then this becomes the integral, I guess I really should have a du here on the end of that last line. And so notice that that's the whole du. And so this becomes the integral of 1 over u du. And so this then is the natural log of the absolute value of u plus a constant. And so then the integral of secant x dx is equal to the natural log of the absolute value of secant x plus tangent x plus a constant. And this is a formula we want to commit to memory. You could prove or calculate the integral of the cosecant function using a similar technique. We've been focusing on the natural log function, but we could really differentiate any logarithmic function. We just have to use a little bit of ingenuity. So if we're asked to differentiate y equals the log base a of x, well, I can write that as y equals the natural log of x over the natural log of a, using the change of base rule that we've seen in a previous section or course. And so notice then I could write that as 1 over the natural log of a times the natural log of x. And so that's just a multiple of the natural log. So then y prime would be 1 over the natural log of a times 1 over x. And we often write this as 1 over x natural log of a. All right, so for example, if I wanted to differentiate f of x is equal to the log base 5 of x e to the x, I can think of this function as the natural log of x e to the x over the natural log of 5. Using some properties for logarithms, I can further think of this function as 1 over the natural log of 5 times, let's see, I'll use brackets. I'll just leave it alone. I can write this as the natural log of x plus the natural log of e to the x. Still, simplifying this further, f of x, 1 over the natural log of 5 times natural log of x plus x. The natural log of e to the x is just x. Now I'll calculate the derivative. F prime of x, 1 over the natural log of 5 times 1 over x plus 1. So that actually turns out to be very simple if you use some properties of logarithms. We can also differentiate the general exponential function using a similar change of base in a sense. If we have y equals a to the x, then I can write this using sort of a change of base as y equals e to the natural log of a to the x. So I'm really just using a cancellation property. E to the natural log of a to the x is just x, is a to the x. So I'm just doing that in reverse. But now I can rewrite this, if I really wanted to, as y equals e to the natural log of a times x, using my properties of exponents. Now, notice that e to the natural log of a is a constant. And so I have now, or it's just, okay, I'm going to start this over. All right, so now if we want to differentiate y equals a to the x, a general exponential function, we're going to use some cancellation properties. So I can rewrite y equals a to the x as y equals e to the natural log of a to the x. All right, so then I can further write this using properties of exponents as e to the natural log of a times x. Power to a power, we can multiply exponents. And so now I've written this as an exponential with base e, and we know how to calculate those derivatives. So then y prime would be e to the natural log of a times x times the derivative of the exponent, so times the natural log of a. And notice that this was just what we originally started with, a to the x. And so then y prime would be a to the x times the natural log of a. So that's how we calculate the derivative of the general exponential function. So, for example, if f of x is equal to 10 to the x, then f prime of x would be 10 to the x times the natural log of 10. If y of t is 2 to the tangent t, then y prime of t would be 2 to the tangent t times the natural log of 2 times d by dt of tangent t. That's from the chain rule. And so then y prime of t would be 2 to the tangent t times the natural log of 2 times secant square t. Now, if we want to integrate a general exponential function, so say for example we have the integral of a to the x, we use the same basic idea in that I can rewrite this as the integral of e to the natural log of a times x dx. And now I make a substitution. If I let u equal the natural log of a times x, then du would be the natural log of a dx. So I need to bring in a natural log of a on the inside and a 1 over natural log of a on the outside. And then this becomes 1 over the natural log of a times the integral of e to the u du. And so that's 1 over natural log of a times e to the u plus a constant. And so then we get 1 over natural log of a times, now e to the u, that would be e to the natural log of a times x, still plus a constant. And again, that was our original sort of substitution. And so we get 1 over natural log of a times a to the x plus a constant. Now, of course, you don't have to go through this every time. You can memorize this. If you don't memorize it, you should know the technique on how to approach this sort of exercise. So, for example, if I have the integral of 5 to the x dx, I can just go and say, well, this is 1 over the natural log of 5 times 5 to the x plus a constant. Alright, so now a technique called logarithmic differentiation. This is a technique that can be used to calculate derivatives of complicated functions, and when the variable is present in the base and exponent of a function. And the idea here is to take the natural logarithm of both sides of the equation, then implicitly differentiate with respect to x, and then we'll solve for dy dx. Alright, so here's an example. We have y equals the square root of x times e to the x squared times x squared plus 1 to the 10th power. Now, could we differentiate this using our traditional techniques? Absolutely. We'd have to use the product rule along with the chain rule a couple different times, but we could do it. It would take us an hour, but we could do it. So instead, here's another approach. I'm going to rewrite this by applying the natural log to both sides of the equation. Now, since I've done this, I can rewrite this equation as the natural log of y is equal to the natural log of the square root of x plus the natural log of e to the x squared plus the natural log of x squared plus 1 to the 10th power. Now, I can manipulate some of this on the right-hand side. The natural log of the square root of x, well, that's 1/2 times the natural log of x. The natural log of e to the x squared is just x squared. And the natural log of x squared plus 1 to the 10th, well, that's 10 times the natural log of x squared plus 1. Now I will differentiate. I'll apply d by dx to both sides of this equation. So d by dx of natural log of y would be 1 over y times dy dx. Right-hand side, d by dx of 1/2 natural log x. That would be 1/2 times 1 over x, 1 over 2x. d by dx of x squared, that's a 2x. d by dx of 10 times the natural log of x squared plus 1, that would be 10 times 1 over x squared plus 1 times the derivative of x squared plus 1 is 2x. Alright, so now I want to solve for dy dx. Oh, I need the dy dx by itself. Well, to do that, I'd have to multiply both sides by y. So dy dx would equal y times that whole thing. So let's see, I'd have a 1 over 2x plus a 2x. Simplifying that last term, I'd have, what, a 20x over x squared plus 1. And now all we do is substitute our original y. So then dy dx would equal square root of x times e to the x squared by x squared plus 1 to the 10th times 1 over 2x plus 2x plus 20x over x squared plus 1. Don't try to simplify that. Just leave it alone the way it reads. What if we were asked to differentiate y equals x to the cosine x? Well, you might say, well, is it just cosine x times x to the cosine x minus 1, right? Oh, wait, you can only use that rule if the exponent is a number, a constant. Cosine x is not constant, so you can't do that. So here we have the variable in both the base and the exponent. And so to differentiate a function that looks like this, we use the logarithmic differentiation idea. So I'll apply the natural log to both sides of this equation. And so then the natural log of y would equal, I can bring that exponent down, cosine x times natural log x. Now I'll apply the differential, right? d by dx, d by dx. So 1 over y dy dx is equal to, now I'm going to have to use a product rule here. So I'd have cosine x times the derivative of natural log x is 1 over x, plus the derivative of cosine x is negative sine x times natural log x. Now I'd multiply through by y, so dy dx is equal to y times cosine x over x minus sine x natural log x. And y is, from the original statement, so dy dx would equal x to the cosine x times cosine x over x minus sine x natural log x. Let's see one more example of this logarithmic differentiation technique. So here we're asked to differentiate y equals sine x to the natural log x. Alright, so applying the natural log to both sides of the equation, then the natural log of y is equal to the natural log of x times the natural log of sine x. Differentiating with respect to x both sides of the equation, yields 1 over y dy dx is equal to, now let's see, I'm going to have to use a product rule and a chain rule. Alright, so I would have then natural log of x times the derivative of natural log of sine x. That would be 1 over sine x times the derivative of sine x is cosine x, plus differentiating the natural log x, that's a 1 over x, and times, leaving the second alone. Multiply through by y. dy dx would equal y times, now I can clean this up a little bit, I've got a natural log x here, 1 over sine x times cosine x, that's cosine x over sine x, that's a cotangent x, plus natural log of sine x over x. And writing this entirely in terms of x, dy dx would equal sine x to the natural log x times natural log x cotangent x plus the natural log of sine x over x. Alright, that concludes this section.